Welcome to videos on RF integrated circuits. So this is the second part of RF ICs. So let us have a look at what is this linearity of RF ICs. So we know that when we actually increase the input voltage, the output voltage will also increase. So you can see the ideally, so as we are keep on increasing the input power, the output power should be keep on increasing because this slope is actually the slope with respect to the gain of the amplifier. Assume that if the gain of the amplifier is 10, if I apply 1 watt, so having a DC offset of some watt voltage over here, so from this watt onwards, so even though when you have a zero input power, we have a DC offset of some watt. So after that, whenever you actually increase the input power by some value, the output power is also keep on increasing. So ideally speaking, this output power should increase. So as the input power is increasing, and it should continue with this dotted line as it is shown here. But ultimately, what happens is in the case of a RF circuits, or in case of any circuit have which involves a semiconductor circuit, semiconductor components, the output voltage starts saturating after some level. You can see now as the input voltage is increasing up to certain point, output voltage is also increasing. After some point, you can see it becomes gets saturated, and you have a saturated output voltage for input voltages anything beyond uh, this particular value of input power. Now you can see this we call it as it is got saturated. The most important region of IC operation would be up to what range the amplifier works like a linear amplifier. So this is the linearity over here. So we are supposed to operate the circuit only in the linear region, because in the saturated region we're going to get the output voltage which is not the desired one. Because of this non-linearity, we define one parameter called as 1 dB compression. So in order to just define what is this 1 dB compression, so we are again considering the same linearity curve. So this is the output power, this is the input power. Just have a look at how does this dotted line would have gone if it was an ideal amplifier. This would have went like this. You can see this is now gets saturated here. So there is a particular input power. You just consider this is a input power. So if you consider an input power of this P1, ideally the output power would have been this, but practically we are having an output power of bit reduced value. Now you can see this 1 dB compression, as the name itself indicates. If the ideal amplifier would have been there, so we would have had a power P here, but actually we are having, this is the power. So how much the difference between the ideal power and the actual power? It is 1 dB. So delta difference in the dB is delta difference in the power of the output is 1 dB. It is the input power at which we have this 1 dB compression of the output voltage with respect to the ideal one is called as the 1 dB compression. This 1 dB compression will refer to the input power at which we get an output voltage which is 1 dB less than the ideal power that would have been got in case of an ideal amplifier. So let me just again repeat. So this dotted line happens to be the output power if an amplifier is an ideal amplifier. Now practically we're going to have a saturated output power over here. Now you just look at, okay, at this point, suppose if you take this power which is P1 here, at this point, the expected value and the actual values are same. So that's why this is not a, there is no compression here. So there is no compression here, there is no compression here. The compression started here. I can see expected is this much, we have an actual power of this much. Expected is this, actual is this. So as we keep on going here, now this is the expected, we are having this much power. So just keep on finding out the difference in the actual and the expected. This is the actual, this is expected. For a input power, that difference happens to be 1 dB. Where does this 1 dB difference comes, that input power happens to be the 1 dB compression power. So this 1 dB compression power is actually corresponding to the input voltage. At what input voltage I will going to get an output voltage 1 dB less than the actual power. So that's what is known as 1 dB compression. This actually refers to the input power at which I am going to get 1 dB less than the ideal power. Similarly, this IIP3, as the name itself indicate, IIP3 is this expansion of this IIP3 stands for, first I stands for the input, second I stands for the intercept, P stands for the point, 3 stands for the third harmonic. It is input intercept point of third harmonic. I'll repeat, input intercept point for of the third harmonic signal. Let us consider the y-axis is in terms of output power, which is specified in terms of dBm. We will try to find out what is this dBm is, how dB is different from dBm, and we have an input level again in terms of dBm. You see this line which is having a square is the actual output power, and this one with a cross is a third order product. So we can see this is the actual power and this is the third harmonic of the same input signal. You can see the output signal for a third harmonic frequencies keep on increasing fast compared to the fundamental frequency. As we know that this is slowly increasing, this is increasing very fast. Where does the fundamental and the third harmonic meet? So this what is, there is an intercept point of the fundamental and the third harmonic, they are meeting here. So the corresponding input power, where does the output of the fundamental and the output of the third harmonic will coincide is nothing but input intercept point. Again I'll repeat, input intercept point is that input power at which the fundamental frequency, the output power of the fundamental frequency and output power of the third harmonic frequency meet each other. So this is what is, in this particular case, IIP3 happens to be 10 dBm. So why this point is very important? Because if the input power is more than 10 dBm, we can see the third harmonic dominates than the fundamental one. So it is not advisable to increase the amplitude of the input power beyond 10 dBm, because any input power more than 10 dBm will want to have the third harmonic of the fundamental signal overtaking the actual fundamental signal. So that's why this third harmonic intercept happens to be a very important parameter in case of RF circuits. So this will actually give an indication of up to what the power we can increase the input power, so that we will not get the influence of third harmonic will not be too much. So if the input power is more than the IIP3, then third harmonic will dominate the output power rather than this fundamental power. Let us see what is this dBm stands for. So dBm, it is the power measured with the reference of 1 milliwatt. So meaning to say, dB we know that it is okay, in terms of power it is 10 log of 1 watt. So 10 log of 1 watt happens to be dB. If you want to specify, because in case of RF we'll be dealing with very small powers, instead of specifying the power in terms of 10 in terms of dB, we put it in terms of dBm. Only difference is that in case of the power expressed in terms of dB, the reference is 1 watt. In case of dBm, the reference is 1 milliwatt. Why we are going for 1 milliwatt is because the power that is handled at RF frequencies are very small in magnitude. So that's why this 1 milliwatt corresponds to 0 dBm. So similarly, we have of course 0 dB corresponds to 1 watt. Similarly, 0 dBm corresponds to 1 milliwatt. So this X, which is in terms of milliwatt, so can be of course X dBm. X dBm can be written as 10 log of to the base 10 actual power in terms of 1 milliwatt. So we will take an example. Supposing that you have 1 microwatt of power. So 1 microwatt of power will be written as minus 30 dBm. Similarly, 40 dBm corresponds to 10 milliwatt. Similarly, 3 dBm corresponds to 2 milliwatt. So suppose we want to have, assume that you want to find out what is the power of this 40 dBm. So substitute this X as 40 here. So it is 40 divided by 10 happens to be 4. 10 power 4 into 1 milliwatt happens to be 10 milliwatt. Sorry, this will be, sorry, there was a small glitch in this typing error. So this 40 dBm, so as we can see here, so this X is actually 40 dBm. So let me substitute X as 40. 40 divided by 10 happens to be 4. 10 to the power of 4 into 1 milliwatt happens to be 10 watt. So this 10 watt will be represented as 40 dBm. Similarly, we can express the watt in terms of dBm. So as we know that 1 microwatt, so we are substituting this P as 1 microwatt. So it is 1 microwatt divided by 1 milliwatt. So which happens to be a ratio of 1 milli. So 10 log of to the base 10 1 milli happens to be minus 30 dBm. Meaning we are expressing very small powers in terms of dBm. So dBm can also be expressed in terms of watts. So similarly 3 dBm happens to be 2 milliwatt. Meaning to say this X is expressed in terms of dBs, this P is expressed in terms of watt here. If okay, if the value of X is given in terms of dBm, we can actually get the power by substituting this as 1 milliwatt multiplied by 10 to the power of X dBm divided by 10 happens to be the actual watt. If you have been given power in terms of watt, we can actually find its dBm corresponding to this power, which is in terms of watt, can be expressed in terms of dBm. So these are the three examples to state how a microwatt can be represented in terms of dBm, how a dBm can be expressed in terms of watt. So how does a dBm can be expressed in terms of watt, of course in terms of milliwatt also. So these are the few RF amplifier specifications. So you can see now we have a frequency ranging from 0.1 gigahertz to 10 gigahertz. Gain varies from 10 dB to 40 dB. 1 dB compression varies from 5 to 20 dBm. The noise figure varies from 2 to 8. IIP3 varies from 20 to 30 dBm. The isolation gain varies from 10 to 30 dB. These are the typical values of a RF amplifier. VSWR ranges from 1.22 to 2.2, and we have the input impedances ranging from 50 ohm to 100 ohm. The amplitude matching varies from 0.05 to 0.3. The phase matching would be from 0.1 to 2 degrees. The DC power varies as per the requirement. So this is an example of MNA RF amplifiers. You can see there are different models specified here, and their operating frequencies are given. So gain is specified in terms of dB. 1 dB compression at 5 volts is given for different models over here. The noise figure is also specified. IIP3 dBm at 5 volt is specified. You can see these are the different IIP3, that is intercept point of the third harmonic is given here. The isolation gain is also given here. The current, the DC current is also specified here. So depending on the application, we can choose the desired model of an amplifier. So this is a varieties of frequencies, other parameters being specified. So depending on the supply voltage and all those things.